What specific problem does your proposed method address regarding the phenomenon of grokking in LLM pretraining? And why is this problem significant in the context of existing research?
Our proposed method addresses the problem of understanding the delayed generalization phenomenon, known as grokking, during the pretraining of large language models, LLMs. Specifically, we investigate how and why generalization occurs long after the training loss has plateaued, which challenges the conventional belief that convergence in training loss equates to achieved generalization. This problem is significant because existing research has primarily focused on smaller models and simpler tasks, often overlooking the complexities of real-world data and the one-pass training paradigm typical in LLM pretraining. By introducing metrics that quantify the dynamics of internal pathways in MO architectures, we provide a more accurate and efficient means to monitor generalization, which is crucial for model developers aiming to improve training efficiency and performance. Our findings reveal that generalization does not automatically follow loss convergence, highlighting the need for deeper insights into the internal mechanisms that drive learning in large-scale neural networks.
How does the proposed method or algorithm work? Illustrate the process step by step, particularly focusing on how you track the dynamics of expert pathways during training.
The proposed method tracks the dynamics of expert pathways during training by analyzing the routing patterns in a mixture of experts, MO architecture, specifically focusing on two key metrics, pathway similarity and pathway consistency. First, we identify a subset of training samples termed grokking data, which have achieved stable low loss at various checkpoints, allowing us to isolate samples that reflect robust learning. Next, we compute the routing pathways for each input, which are the ordered sequences of selected experts across the MO layers. We measure the similarity of these pathways using the edit distance metric, which quantifies how closely related the routing patterns are across different inputs. Additionally, we assess the consistency of a single input's pathway by calculating the average cosine similarity between consecutive layer embeddings, indicating how smoothly the model transitions between expert selections. By tracking these metrics over time, we can observe how the model evolves from individualized computations to more structured shared pathways, providing insights into the memorization-to-generalization transition during training.
Can you provide a simple yet illustrative example of how your metrics for measuring pathway complexity are applied in practice, demonstrating the transition from memorization to generalization?
In our study, we applied two metrics to measure pathway complexity: the edit distance between different samples' pathways and the consistency of selected experts' embeddings across layers. For instance, during the pre-training of the OLMOE model, we observed that initially, the pathways for different inputs were highly similar, resulting in low edit distances. As training progressed, the pathways diverged, indicating individual memorization of samples. However, once the training loss plateaued, we noted a reversal in this trend, where pathways for semantically similar inputs began to converge again, reflecting a transition to shared, structured computation. This shift was accompanied by an increase in pathway consistency, suggesting that the model was refining its internal representations to facilitate generalization, thus demonstrating the transition from memorization to generalization effectively.
What are the theoretical or practical benefits of using your method compared to traditional metrics, such as training loss, in understanding generalization in LLMs?
The theoretical and practical benefits of our method, which utilizes pathway complexity metrics, significantly surpass traditional metrics like training loss in understanding generalization in LLMs. Firstly, our metrics, pairwise pathway similarity and single-sample pathway consistency, provide a more nuanced view of the model's internal dynamics, revealing how expert routing patterns evolve during training, which is crucial for understanding the transition from memorization to generalization. Unlike training loss, which can plateau while generalization performance continues to improve, our metrics correlate strongly with test accuracy, often exceeding 0.97, indicating their reliability as indicators of generalization readiness. Additionally, These metrics can be computed without requiring a test set or model fine-tuning, making them efficient for real-time monitoring during pre-training, especially in resource-constrained environments. This positions our approach as a valuable tool for model developers, offering insights that traditional loss metrics fail to capture, thereby enhancing the understanding and optimization of LLM pretraining processes.
How did you validate your method, and what experimental design and datasets did you use to test its effectiveness?
To validate our method, we conducted a comprehensive analysis of the training dynamics of the OLMOE model, a 7 billion parameter mixture of experts, MO architecture, during its pre-training phase. We utilized a diverse set of real-world tasks, including arithmetic reasoning, code generation, common sense question answering, and domain-specific knowledge retrieval, to ensure the generalizability of our findings. Our experimental design involved tracking the Grokking times of training samples, which allowed us to categorize them based on their learning stability and relate this to downstream generalization performance. We introduced two novel metrics, pathway similarity and pathway consistency, to monitor the internal dynamics of the model, and we established strong correlations between these metrics and test accuracy across various tasks. This empirical evidence demonstrated that our metrics effectively captured the transition from memorization to generalization, validating their utility as reliable indicators of model performance during pre-training.
What significant results did you achieve using your proposed method, and how do these results enhance the understanding of grokking and generalization in LLMs?
Our study achieved significant results by empirically verifying that grokking occurs during the pre-training of large language models, LLMs, specifically the OLMOE model, and demonstrating that this grokking is local and asynchronous across different data groups. We introduced two novel metrics, pathway similarity and pathway consistency, that effectively track the dynamics of memorization to generalization transitions without requiring test data or fine-tuning. Our findings revealed that as training progresses, the model's internal pathways evolve from individualized to increasingly structured, indicating a shift towards shared knowledge and better generalization. Notably, we established strong correlations between these metrics and test performance, highlighting their utility as reliable indicators of generalization readiness. This work enhances the understanding of grokking by elucidating the internal mechanisms that facilitate the transition from memorization to generalization, challenging the reliance on traditional loss metrics and providing practical tools for monitoring LLM training dynamics.